section 4.2 is titled Area, and it's going to feel like that we have taken a complete detour and it looks nothing like what we've done in the other sections. I'm going to just tell you that right up front. You're going to be like, what are we doing? It's okay. We'll make connection to what's going on between these sections as we move forward. But for today, we're going to take our attention to something called sigma notation. You may or may not have seen this before, and if you continue in calculus to Calc 3, you will see it again. So sigma notation is a way of showing that we're adding a bunch of things together. The things that we're adding together are the terms A1 to AN. And the notation looks like sigma. The I equal 1 to N, 1 is underneath and N is at the top, tells you where we're starting. N is 1 where we're starting. I is 1 where we're starting. N is where we're ending. That's the top value. And A sub I are the notation pieces, right? Those are the things we're adding together. So what's on the left really is this summation. So what we're doing is we're doing a shorthand notation, right, for summing or adding a bunch of things together. A little bit of vocab here. I is called the index of summation. A sub I is called the ith term. And the upper and lower bounds are what we call the n and the 1. So 1 is our lower bound, n is our upper bound, and they are below and above the sigma. Okay, so we're going to do an example where we're going to sum just a short number, a small number of these together. So we have the ith term being 3i minus 2. And this sigma notation tells us we're going to start at 1 and we're going to go to 6. So what that means is I'm going to have an a sub 1, an a sub 2, all the way to a sub 6. Okay, and I'm going to add all these together once I get their values. So when I look at finding a sub 1, it literally means put 1 in for I. So I have 3 times 1 minus 2. So what is 3 times 1 minus 2? It's 1. And then I'm going to do 3 times 2 minus 2, which is going to give me what? 4. How about 3 times 3 minus 2? 7. We're going to do one more and we're going to pause. What is 3 times 4 minus 2? 10. Do you notice a pattern happening with the values that are showing up? 1, 4, 7, 10. They're increasing by 3. Why is that happening? Because it's 3i, right? It's 3i. It's just like having 3x, 3 being the slope of an equation, right? If 3 is the slope, every time you go up 3 and over 1, you're going to get another point on the line. This is the same thing. Once you notice a pattern, and it's nice on this one because it is linear, you're welcome to just shortcut it and write those values down. What should be the next value without even calculating it? 13 and then 16. So if you happen to notice a pattern going on, and sometimes you're not going to, but feel free to just shortcut to finding those pieces. And then what we're actually doing is we're actually finding the sum of all those values. So we're doing 1 plus 4 plus 7 plus 10 plus 13 plus 16. And what do we get? What is it? Is it 41? I have 51 written down. Am I wrong? Is it 51? Okay. But you got 51? Okay. Double check, make sure it's 51. It might have been the 10 got left out. Okay, cool. All right, it's 51. Okay, this is arithmetic, right? It's arithmetic with some funny notation at the beginning. That's really all we're doing on this problem. Agreed? Okay. What we're going to do next is we're going to analyze, or not analyze, but at least become aware of some summation formulas. So as we're taking a look at these formulas, we have formulas that look like constants. We have formulas that look linear, right? Just I. That's equivalent to having like y equal x. We'll have formulas that look quadratic, like I squared. And we'll have formulas that look cubic, like I cubed. And if I know what the formulas are, which we can memorize them, they're not that difficult, we can actually shortcut finding all of the terms and adding them together by applying a formula to it. It's kind of like when we learn about the limit definition of derivative and everybody's like, would we please stop doing limits and just get to those shortcut rules? It's like that, okay? So let's take a look at what these shortcut rules are. And I'm going to give you names for some of these as well. Actually, I think they're written on your paper. The first one, if I'm adding together C a bunch of times, C plus C plus C plus C plus C n times, that's just C times n. And this one is actually called a sum of constants. The next one is the equivalent of adding together something like 1 plus 2 plus 3 plus 4 plus 5, all the way until you get to whatever n is. So if n is 7, you stop at 7, right? And the way that we actually get the summation here is we take n and we multiply it by 1 bigger, n plus 1, and we divide by 2. And not necessarily in this form, but this problem, this formula, this process for doing so, was actually discovered by a gentleman named Gauss, or at least he's credited with it. And he did it when he was 6 years old. Not with these letters, not with these numbers, but what happened was his teacher gave him busy work, as some teachers might, to keep the little kids occupied, and said, let's add the numbers from 1 to 100 together. And that should take them a while, and it would, right? 1 plus 2 plus 3 plus 4 plus 5. Unfortunately, Gauss did it very quickly, and he figured out a pattern of what was going on, and it evolved eventually into this formula, okay? So this is actually called a sum, or this is the sum of the first n positive integers. That's what it is. The next one is I squared. So this one is actually n times n plus 1 times 2n plus 1, and it's divided by 6. Sorry, I don't have any fun history on this one. Okay. So when I have I squared, this is what we would actually be able to use as a shortcut. This is the sum of the first, I didn't say that right, the sum of the squares I'm going to keep moving the word first over, of the first n positive integers, just like the last one. So this is summing things like 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, right? And this is the shortcut. And the last one that we're going to do is n squared times n plus 1 squared, and it's over 4. And in much the same way, this is the sum of the cubes of the first n positive integers. So 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. Now, the last one we did was not very big, and it was not very difficult. It only went to the number 6, and it wasn't terribly complicated. But I'd like to show you how you could use this formulas in that case, just so that you can see we do get the same answer. Okay? So I'm going to flip back to the other screen, and we're going to take a look at this problem with these pieces in place. What I'm actually able to do with these formulas is break things apart in very much the same way that we do with derivatives and with limits. These are all related ideas. Is that I can take this same summation. It's I equal 1 to n each time, so I'm going to leave that off for a moment because that's not going to change. But I have 3i, so there's the 3 can come out to the front like a constant multiplier, and the I can be inside. And then I have the summation of 2, and I put a subtraction sign between them. Okay, so I'm breaking them apart. What this tells me is that this piece right here matches the description over here of the second one. It should be n times n plus 1 over 2. But, oops, sorry, but what was n? 6, right? So I have the 3 in front, and then I have 6 times 6 plus 1 over 2. And then I have minus. And then the first one, the -2, which is second listed, but is the first formula here, is a constant. It says I take that constant, namely the 2, and I multiply it by n. So this 2 gets multiplied by n, and n is 6. Okay, so I'm not suggesting that this is easier than what we did. I'm just showing you that it's going to give me the same answer. So if I take 6 times 7, what do I get? 42 divided by 2, 21. And then I would have 3 times 21. What is 3 times 21? 63. And then I'd have 63 minus 12. And what is 63 minus 12? 51. I get the same thing. Okay? So that is not a proof by any stretch of the imagination, but it's at least an example showing that it worked for this particular problem. All right, so we're going to take a look now at some examples that we wouldn't necessarily want to do this for, because I don't have just 6 terms I'm adding together. How many would I have on this one if I were trying to do it the other way? 16. And I don't know about you, but I don't want to find 16 terms and then add them together. If there's a shortcut way to do it, that would be nice. And there is, and it's very much like the problem I just did. I can take the 5. Let's first identify, what is n? Yeah, n is 16. We're going to need that. And as I'm working through the problem, I'll be more careful this time because I'm actually doing the problem that I'm asked to do. This is I equal 1 to 16. And I can pull the 5 in front and leave the I inside. And then I have minus, and the summation of 4. And it's I equal 1 to 16. So the 5 stays in front. I have n, which is 16, times n plus 1, which is 17, over 2. Minus 4 times n, which is 16. And all I'm doing is applying the pieces of these formulas over here to doing that. And then feel free to grab calculator. We're going to do 16 times 17 divided by 2, and then times 5. Then you're going to subtract the 4 times 16. That's all arithmetic your calculator would be happy to do for you. And what will you get? Some of you are grabbing one out, so we'll wait. Do you have a value? 616, that's what I have as well. Okay, so that's a linear one, like the first one I did. The more complicated and the bigger the numbers, the harder it becomes. Now, what does n equal here? What is it? 140. Oh, I'm sorry, I used bad notation. No, you're fine. I see what you said for now. Gotcha. Okay, the notation in the problem, I'm using it because I want you to see that sometimes they change the letters up, and they did here. They've used n as their limits of, like their integration, not integration, but their interims, right? They're using it instead of I. If that bothers you, and it's kind of going to bother me, you can change it so that we can still keep thinking of n as the way we've thought of it. So because it's easier to change it to a k, I'm just going to write it as k, but feel free to write it as an I if you wish. So I'm going to adjust those and make them k. But do recognize that if there's something inside of WebAssign where you're using a letter and the letter is still present, make sure and stick with the letter that they give you, because they will count you wrong if you've changed the letter. So for the purposes of what we're working with, I'm changing them to Ks. And so we're going to look then at the n, that is the top one, the upper bound being the 140. There's something else weird, though, that hasn't happened on either of the other two problems, besides the fact that the 140 is much larger. What else is weird? That's really important, Daniel. We're not starting at 1. And all these formulas are based on us starting at 1. Are you with me? So I can't just decide I'm going to start at 4 and the formulas perfectly match. Something has to give. So what gives? Well, what happens is I'm just going to write it out here. I'm going to change it so that it starts at 1. Otherwise, I can't use my formulas. So I've got k times k minus 1. Actually, let me multiply it out. This would be k squared minus k, right? But if I did that, I've introduced more summations than I had. I've added in an A1 and an A2 and an A3 that really aren't there. Agreed? I've added them in because I changed the 4 to a 3. So in order to compensate, I need to subtract them off. And I can do that at the end, just like that. So whatever A1 is and whatever A2 is and whatever A3 is, I'm going to subtract them off at the end. So there are 3 of them I'm going to calculate, but I'm not going to calculate, 137 of them. That would be terrible. 16, we could have done it on the last problem. 137, now we're like Gauss's teacher. We're not going to do that, okay? All right, so let's start with, I'll put these in parentheses just to identify that they're separated out. The formulas and their pieces. So I have k equals 1 to 140 of k squared. And it's minus k, or the summation from k equal 1 to 140 of k. And then I'm going to subtract off A1, A2, and A3. All right, so the formula over here for k squared is the I squared one. I take n times n plus 1 times 2n plus 1. So n is 140. N plus 1 is 141. What is 2n plus 1? 281, thank you. And I'm dividing it all by what? 6. The formula on the previous page is a 6. The next one, I take the same n, 140, and n plus 1, 141, but I'm dividing it by 2. A1 literally means taking the expression I was given, and you can take it in either the form where it's factored, if you wish, or the form where it's distributed out, and putting in the number 1. So if I put in the number 1, what do I get? It's 0. So A1 is actually 0. How about if I put in 2? Yeah, it's actually 2. So 2 squared minus 2 would give me another 2. And what if I put in 3? 3 squared minus 3? I get 6. So at the very end, I'm going to end up taking off a 0, a 2, and a 6 from whatever I have. All right, so each of those calculations, you can stick them into your calculator, right? It can multiply 140 times 141, so forth, divide by 6. Same thing in the middle, divided by 2, and then we take off 8 at the end. And if we get all those pieces in there properly and so forth, it will become 914,612. Okay, is that all right? Okay, so I'm going to keep going as far as I can today, and what we're going to do when I get to the end is I'm going to post a video for the last pieces that I don't get done, because we do have a quiz on Monday, and because I just moved your gateway up to Wednesday, we need to make sure we take the quiz on Monday, so we're not doing 2 quizzes on Wednesday, because that'd be like the whole class period. So we're going to keep going as far as we can. Area. This is part of our connection of what we just did back into what we were going to be looking at. The next part's going to be next class period. The area of a plane region. The area of this region, that is from A to B, and if I were to mark off these pieces, like so, and shade it all in. This is the area it's talking about. The area of this region can be approximated using rectangles. But there are 3 different approaches specifically that we're going to look at anyway for rectangles that we can use to approximate the area of this region. So let me draw in what I mean by doing this area with rectangles. And I'm going to do 4 rectangles, not because it's a good picture, but because it's a good enough idea without the picture becoming overly complicated. So if I split the region in half, and then I split it in halves again, and I were to draw in vertical pieces, you can imagine that there are rectangles, but the rectangles don't have a straight top on them, right? There's this sort of variable shape at the top that makes it not actually a rectangle, but if you had more of them, you could get closer to rectangles. So don't keep drawing, but if you split those in half again, and if you split them in half again, eventually the tops of those rectangles would get closer and closer to looking like they were actually rectangles. Agreed? So all my pictures I'm going to do are going to have 4 rectangles because they're easier to work with for the drawing and to talk about what's going on. These locations where I'm splitting them at the bottom are going to be called x sub zeros. So that's the sub zero or sub notation that we saw in the previous ones where we had a sub i's is showing up here. This would be x1 and x2 and x3, and the b value ending at x4. And the width of the rectangles, right here, is called delta x. Delta means change in, so it's the change in x, and it can be found by taking, oops, didn't mean to put that there. Try that. The ending point, which is b, or x4, minus the beginning point, which is a, or x0, and dividing it by however many rectangles we're wanting. So b minus a over 4. So the ending location, the beginning location, and dividing by however many rectangles I'm creating. I'm showing you 4 rectangles, but you can certainly do different numbers of rectangles. The same picture can be drawn 3 ways. One of them using left endpoints, one of them using right endpoints, and one of them using midpoints. So I'm going to draw the same picture multiple times, split in halves and in halves again, with those same vertical pieces showing up. And this is still, make sure I've got mine listed the same way, x0, x1, x2, x3, x4. And we're going to do the same picture on all my graphs. So you can copy yours. I'm going to actually copy paste so that they're identical, and hopefully the pictures will be a little bit more spot on from graph to graph by doing so. All right, those are pretty close. All right, so left endpoints, what does it mean? Well, it means that the interval that I've selected from x0 to x1 is going to use the point that's on the left side to determine the height of the rectangle. So what does that look like? Well, it looks like this. This is my left-hand endpoint, and I draw straight over and I draw straight down, and now I have a rectangle that's clearly not exactly the area. It's a little bit too much, right? But I mean, it's close. And I can do the same thing with the next interval. From x1 to x2, I use the left-hand endpoint, and I draw a straight line over. This one is not near as good as the last one. It is overestimating it by more than the first one did. The third one, when I draw it, notice I've actually got an underestimate this time. So the overestimates and underestimates tend to balance each other out for many equations, though not for all. And then I have a vastly underestimated piece over here. So the area, if I calculate this now, will be the area of these 4 rectangles, some of which are overestimating the area and some of which are underestimating the area. And these are my left-hand endpoints. Now, taking a look at doing that, what happens is that each of these widths are the same. So how do I find the area of a rectangle? You know this. Base times height, length times width, whatever notations you're thinking of. I need the 2 dimensions and I multiply them, right? Well, all of these have the same dimension, delta x. So when I'm finding the areas here, I'm going to call it L of x because I'm using the left-hand endpoints. Just make sure L doesn't look like a 1. And I'm going to take the width, delta x, times the height. Well, what's the height of the first rectangle? Well, it's that dot that I put at the top of the little bar that's left at x0, right? Well, what is that? Well, it's the function value at x0, so it's f of x0. Plus, I do the next one. Well, its width is delta x as well, but its function height is at x1. I do delta x again, and the function height is at x2. One more time, and the function height is at x3. You might be asking, well, what about x4? Well, I didn't do a function with the dot at x4. I did the other 4. So these are my 4. But notice, oops, that's a delta x. Notice there's delta x in every single problem. So thinking in terms of algebra, I could factor the delta x out in front. And if I do that, I just have the summation of f of x0 plus f of x1 plus f of x2 plus f of x3. But we just spent the first 2 pages, basically, of our packet here looking at summations of things. Now I have a summation of things. So I'll move down here. I do have the delta x, but then I have a summation, in this case, from I equal 0 to 3 of f of x sub I. Right? Now the right-hand endpoint works just like that. I have the same kind of picture. I've got the same interval pieces, but my endpoints that I'm using on the right side. So instead of looking at this interval from x0 to x1 and using x0 as my endpoint, I use x1. And the height is that height. So now here's my height. The next one I use x2 because it's the right endpoint. And you might be saying, well, aren't I just pretty much overestimating it by about the same amount? It depends on the equation, actually. So when I'm creating my summations on this one, I have the summations that will be starting at x1 and going to x4. So my right-hand summation, r of x, will have a delta x on every point. But the summation from I goes from I equal 1 to 4 now of f of x sub I. Typically speaking, the third one is the most accurate in terms of giving you an area, but it doesn't have a nice compact form really to write it in quite like this, but we can still use it. We use the midpoint. So what we do is we take a point halfway in between and we use that point to be our height. So these are the heights of our rectangles. So again, sometimes they're an underestimate, sometimes they're an overestimate, sometimes they balance the way they're estimating, and it all depends on the function that you're using. So it looks like that. So I'll be finding those heights. In order to find those heights, I actually have to find the midpoint of each one of these and what they are. I don't have a label for doing that, but I do have to find those 4 values. Okay, so actually here's what I'm going to do. I'm going to start the last example. If I don't have a chance to stop it, I'll pause it. I'll finish the video after you guys leave, and then I'll just post it all in one cohesive whole. We'll do it that way. Here's an equation. Our equation is 2x squared plus 5. You know what that equation is. It's an equation of a parabola. Thank you. It's a parabola opening up, and it has a y-intercept of 5. Yes. So if you want to sketch a graph, though you're not required to on the way the question's worded, I don't think, you can do so, and it would look something like this. And I'm trying to make my interval go from 0 to 2. So from 0 to 2, and it tells me I'm using 4 rectangles. That's what n equal 4 is telling me. So I subdivide all of these intervals. This one's 1/2, and this one's 1.5. You can use decimals, you can use fractions. So as I'm looking at the left-hand endpoint, or the right-hand endpoint, or when I'm using midpoints, what is the width of every rectangle? This is not a trick question. What is the width? Thank you. Yes, it is 0.5. The width of all the rectangles I'm going to draw are all going to be 0.5. No matter which endpoint I use, I've got 4 rectangles, the width is 0.5. And if you had something that was a little more complicated to be able to just not see that, you take the ending value 2 minus the beginning value 0. 2 minus 0 divided by the number of rectangles, which is 4 here, gives me 1/2 or 0.5. So 0.5 is my width. So on every single one of these, I'm going to have a width of 0.5. The heights are what's going to change. Okay, so we're at the end of class. I'm going to pause. There's probably going to be like 3 minutes for you to go back and watch to get the rest of this problem written down. All right, picking back up where we left off, if we're looking for the left-hand endpoints, it means that we use the 4 left values. So I'm sorry, put the wrong place. I would start with 0. I would have a function value, and it would draw like this. I would have a function value at 0.5, one at 1, and then one at 1.5. So those would be my 4 values that I would be using. I'll do those in red, and then we'll change the color for the other piece, and hopefully the graph won't get too messy looking. So what I want is I want the function's height at 0, at 0.5, at 1, and at 1.5. And as you're putting those in, you're welcome at that point. I want you to list that out. That is important. List all that out just like I have, but then you're welcome to let your calculator find all those pieces if you wish. You're welcome to write them down as well. If you use those pieces and you find those values, you will get that the area is 13.5. If we use the right-hand endpoint, and I'll use blue for that one, we would use the right endpoint of each interval. So the first interval would actually be using the 0.5 value. And then I'd be using the 1 value. And then 1.5, and then 2. So my heights, the blue dots, right, are representing the values I would have there. So this is f of 0.5, f of 1, f of 1.5, and f of 2. And again, you can use your calculator to find those values and then add them together, multiply by 0.5, you'll get 17.5. The last one uses different values entirely, right? It's using midpoints, which means I actually have to calculate midpoints. So let me use a green, and we're going to find the halfway point of each of our intervals and write those down. So the halfway point of the first interval is 0.25, and then I have 0.75. I have 1.25, and I have 1.75. So those are the heights that I would use on my graph. It would be sort of smack dab in the middle of each of the ones I've done, that green. And depending on the equation, it might actually be exactly half the value, sort of like the midpoint value between the two. It doesn't have to be, it depends on the equation. But so we're finding f of 0.25 now, f of 0.75, f of 1.25, and f of 1.75. Again, make sure you're writing that out. Once you have written that out, multiplied by 0.5, and it is still by 0.5, the width of the rectangle, even though I'm using the midpoints, is still 1/2. And if I multiply that out, add it together and multiply it out, I will get 15.25.